Okay, in this experiment, which is the design part of the lab, you are required to design two types of amplifier. One for JFET, the other one is for BJT. For JFET, it's very straightforward. You can just apply it. Just have to set the VGS so that the gain that you desire will be adjusted according to the RD, and the current will be set by VGS. It's very straightforward. But for BJT, the design process is a bit tedious. Before we can start with the design process of BJT, you need to understand a few things. You need to understand the most important things is the characteristic curve of a transistor. So in this example, you can see that this is a VCE, and then this is IC. So you can see the current is very high, is 100 milliamps, and this is 20 volts. So this is typically for large signal where you are producing a very high current to the amplifier. In your lab, we are using a small signals type of the transistor, something like 2N222A. This is the typical characteristic curve of a small signal transistor. You can see that the current is smaller, 10 milliamps, and the VCE, depending on the type of transistor, can go up to 40 volt or 30 volt, 25 volt before it goes to the cutoff region. So before we start designing the amplifier, you need to understand what is this characteristic curve is all about. Okay, this is the IC and this is the VCE. So this is the cutoff region and this is the saturation region. The slope for this, as I've shown you in the lab manual, the slope for this will tell you what is the gain of the amplifier. If the slope is very steep, means that the gain is small. If the slope is not that steep, means that the gain is medium. If else is a is a high gain amplifier. The problem is that when you have a very low IC current and you have very high VCE or VCC in this case, what you will see is that your amplifier will be very easy to go into the saturation region. This is cutoff region and this is saturation region. So when your transistor is in cutoff region, it will totally off. And you have another one that is not shown in here, which is the safe operating region. So it will go up. So we don't care about that. Okay, now there are many strategies. So if we take a look curve, I just want to show you. If my IC is 6 milliamp and my VCC about 15 volt, you can see that in order for me to bias this thing properly, so I need to go beyond the saturation region. The saturation region is around this, and this is my cutoff region. So this will be the linear region. So now if I want to do this thing, you can see that if I take somewhere around here, and my VCE is around half of the VCC. So it's between half to the 2/3 of VCC. And you can see also that in order to be safe, so this is the biasing current. In order to be safe, I have to make sure that my VB is around 1/3 of VCC. That's typically the idea on how to do the design of a transistor of an amplifier using a BJT. So equipped with this, You can either do your design using a BJT, using a load, by drawing a load line, or just by approximation. So you can see that this is the range. If you set your VCE to be very high, it will easily fall into saturation region, and it has a more swing to the cutoff region. So if you set your VCE to be very low, it will easily switch off the transistor, and it will have high swing to the saturation region. So you have several ways on biasing the transistor to make it as an amplifier. You can have a fixed bias, voltage divider bias, or you can have different kind of biasing technique in designing the amplifier, depending on which one that works and which one doesn't work. If voltage divider doesn't work, you have to change your design into fixed bias, which will give you very high gain but very easy to fall into saturation. Typically, you use a fixed bias when your gain is very high and the signal is very small. The signal is in the range of maybe tenth of milliamps, or maybe less than that, and you need a very high gain. Okay, so for a typical BJT amplifier, NPN, this is what you need. You need your VCC, you need your VBB, you need your RE, you need your RC, and you need your RB. Okay, the current that is needed for this amplifier is set by the RE, because IE approximately equal to IC. The gain of the amplifier will be set by your RC. The input impedance for this amplifier will be set by your RB, and the reflection of RE to the base. So this is basically what you need. And the output resistance is basically your RC. Okay. In your classroom, you know that your gain is given by minus RC over RE plus RE. If you don't bypass this thing, if you bypass this thing, in AC this thing will turn to 0. And you know that your RE is thermal voltage over IC. So typically VT is around 26 millivolt at room temperature. So to make our life easy, I will just approximate this thing to be 25 millivolt for easy calculation. As we've seen from the load line, what is required in this is the VCE. It should be in the range of half VCC to about 2/3 of VCC. How do we choose what should be the range? This thing is varying. We need to adjust the RE that will set our VCE so that we get the gain that we want. So VCE is VC minus VE, and VE is IE times RE. So this is what we need. We can see that basically this is the one that will set what will be our current, and the gain, which is depending on the RE, which is this, depends on RC and the current that we set. Okay, I'll give you one example. Let's say our input impedance or input resistance to be around 33 kilo ohms, or greater, and say my R out is around, say, 2 kilo ohms, and I want the gain to be about minus 100. If you do this thing, how to set? I know that a few things that I have in mind. If I have this thing to replace this, this is my V in, so that I can have a common supply voltage. So the combination of this, say this is R1 R2, so R2 over R1 plus R2 times VCC, this thing should be around 1/3 of VCC. This will give me a ballpark figure of what should I start. And I also have what should be the current that is needed for this amplifier. So I know the AV is around minus 100. If you work out this thing, I will select my RC to be about the same as my output resistance, 2 kilo ohms over small re, and I will have my Re to be around 20 ohms. So I know that my IC should be around 25 millivolt, which is my VT, and my IC is my RE is 20 ohms, so I'll get my IC around 1.25 milliamp. This is to give you some idea. If I set my IC to be 1.25 milliamps, which is around it's around here, and this is my VCC, so you can see that the slope is about this. The problem is that it's very difficult for me to set the amplifier above the saturation region. So I have to push my VCE to the left as possible so that I can get a good swing, because this is around my saturation region already. So this will set as my saturation region. So I just have this. So if I want to change my current, means that I want to increase my RC, I have to decrease my RC, or I have to reduce the gain. So this is not possible, so I have to work with this. I have to do some compensation to compensate which one should I do, and then I have to check whether my transistor is on or my transistor is off. Now I have my VCE is my VCC, which is 15 volt, minus RC. So RC is IC times RC. I need to find what is I need to set minus VE. So this is VC minus this is so now I have my VE, this is VCC, so this is my VC, then this is my VE, so this minus VC, and VCC minus VC, so this will give me what is my RE that is needed. So if I set, minus VCE, if I set my VCE to be very high, 2/3, then you can see that my amplifier will be easily falls into saturation region. If I set my VC E to be very low, less than half, even though it has a high swing, but you can see that my transistor easily switch off because I do not get the basic requirement of the full swing. Okay, if you do all this thing, you will see that RE that is needed is around 3.2 kilo ohms. I need to have my VE to be greater than 4.3 volt. Sorry, less than 4.3 volt. So this is basically the requirement that I need. If you do this thing, this is about 2 kilo ohms. So in your simulation, let the RL to be very high. So let the RL to be 100 kilo ohms. This thing, make it 100 microfarad. So this is the one that you calculate. So this thing you can use around, this will give you a good value. You can put this thing 10 microfarad. So this is the required. Say this is 15 volt. If you adjust this thing, you can see that this will only change the input impedance. It won't change that much the characteristic of the amplifier because the gain is basically set by this. So if you do the simulation for this, you can see that by changing this thing, I can change the gain of the amplifier. So in this case, say my RB as I shown just now, about 33 kilo ohms. So I can set this thing to be 100 kilo ohms, and this thing 50 kilo ohms. So in the lab, you can use 47 kilo ohms. This will give you approximately 33 kilo ohms and above for the input impedance. You set this thing. If you do the simulation for this, you will find that the gain is around 90. So what you need to do is that you have to change this thing, reduce this value, so that you will increase the current. Means that you are changing your VCE to the right of the characteristic curve. If you do this thing, you will reduce the swing. So if you change this thing, you will find that 2.7 kilo ohms will give you approximately 100. You change this thing to 2.7 kilo ohms, and then you will get your gain approximately 100. So set the DC and you use your AC information to do your design of your amplifier. I hope this will help you in doing your lab and understanding how to design a good amplifier.